to it then. Last time, well, I got a little oh, the projector. I'm sorry, guys. I'm forgetting something this morning. Last time I wrote up a question that we got distracted by something else. So it was the one on the left there. So what is that integral? Well, okay. There's two ways to do these. Either you know or can find an antiderivative, or you have to use geometry. Right now, those are the only two tricks on the table, okay? And in terms of how we can find antiderivatives, the techniques we know to do that, there's a gajillion of them. That's basically the only one we have right now, okay? Is guess and check, or maybe a slightly smarter way to do that would be, if we know our derivative rules really well, then we can kind of reverse them, right? So in the same way that, like, I know that sine of 30 degrees is 1/2, what's the arc sine of 1/2? 30 degrees, right? So it's sort of similar with the unit circle stuff, right? If you know the unit circle forwards really well, then you should be able to reverse it, okay? And so what are the rules that we know here? Well, we know the derivative, the basic derivative rules, okay? So not even product, quotient, chain rules, any of those. We know the power rule, we know the derivatives of all the trig functions, we know the derivative of e to the x, logarithm, all of that sort of stuff, right? So if we know those things really well, then we can kind of reverse them. Okay, but do we recognize the square root of 1 minus x squared as something that we've seen when we were doing derivatives? Not really, okay? It vaguely looks like some stuff that we got with like arc sine or whatever, and it turns out that's actually going to be related to it, but it's not at all obvious. Okay, so let's back up a moment and realize that I'm not, like, do I absolutely need an antiderivative to answer this question? No, that is a way to answer the question, but it's not the only way. And the reason is because this is a definite integral, meaning it has numbers at top and bottom. Okay, so what do those numbers mean? Well, if I had an antiderivative, I could plug them in. Okay, but what it means is that I'm looking for the net area that's between the curve y equals the square root of 1 minus x squared and y equals 0, the x-axis, where x runs between 0 and 1. Okay, so let's sketch what that looks like. Okay, any ideas as to what kind of curve the square root of 1 minus x squared is? Not off the top of your head? Nah, not quite. If the square root weren't there, it would be a parabola. So I'll give you a hint. Let me take y, okay, square both sides to get rid of the square root. Now is it more clear? No, better. It's a circle, right? If I add the x squared to the other side, then I get a circle, okay, of radius 1 centered at the origin. Okay, now I'll give you another hint. If you have an equation and you kind of stare at it, okay, so I squared both sides to get rid of the square root. Okay, that was kind of a convenience thing. But what's left is something that involves numbers, x squareds, y squareds, x's, y's, and maybe x times y. Okay, now some of those don't appear in this case, but if you have an equation and that's all that appears are numbers, x's, y's, xy's, x squareds, and y squareds, with some pluses and minuses and stuff sprinkled around. What kind of curve is that always going to be? Guesses. Okay, not necessarily a circle, but what So the problem with that answer is circle is too narrow of a category. What's slightly bigger than the category of just circles? Huh? Yeah, but that's too big, right? We want something in between. Okay, because there's a crap ton of curves out there, and circles are one very special kind. But what's a category that circles are a part of that's not nearly as general as all curves? Okay, ovals, what's the fancier word for that? Okay, ellipses and circles, what other kind of curves sort of are related to those? What is an ellipse anyway? Smushed circle? Yeah. Well, what are those things called? They're called conic sections, right? Yeah, what is a conic section? You take a cone and you cut it, right? Okay, so if I take a cone and I cut it, what kind of curves can I get? I can get circles, ellipses, parabolas, hyperbolas, right? Those are all examples of conic sections. Okay, so if you've got x squared, y squared, xy, x's, y's, and numbers, just those things, it's going to be a conic section. The question is just which one. Is it a circle? Is it an ellipse? Is it a hyperbola? There you have to look at all the details. What are the coefficients? Who's got a plus? Who's got a minus? All that jazz. But if all you just see is a bunch of those things, no powers get bigger than 2, conic section, done. We? No. Okay, so it's a circle, and in our case, because we are going from 0 to 1 in the x's, it's actually just a quarter of the circle, right? Is the part that we're interested in. Okay, so this integral is asking us what is this signed area. Do I need to know how to do the antiderivative to actually know what that area is? No, because what is it? Yeah, what's the area of a circle? Pi r squared. What's the radius here? 1. So, and we've got a quarter of it, so the area is just 1/4 pi. Done. Okay, so basically the TLDR here is more, what techniques do we have at our disposal? We either know our antiderivative rules really good so that we can do them in reverse. Some of that will kind of be guessy and checky, okay? And then the second is geometry. Those are literally the only 2 things that we have on our menu right now. We'll add a third one starting kind of later today. Well, it's going to be some part of a circle. Okay. Now, the fact it was from 0 to 1 also made this easy because let's say that I went from a half to 1 and I was only looking for this orange area. Is there some nice geometry formula for that? Nope. Okay, so then we'd be hosed and we'd have to do it a different way. Okay, but if it's some nice, clean quarter circle, half circle, whole circle, something like that, then it's actually not all that terrible. Okay. All right. So does that kind of make sense? All right. So let's do some more examples here. Let's revisit a problem that we've done already. Actually, 2 of them that we've done already. Let's say that I wanted to do this. Okay. We already did this one, and we did it using geometry because we said y equals x is a straight line, and so the area that we're sweeping out is some sort of right triangle. We don't need calculus to find the area of that triangle, okay? And what did we get here? If we did it geometrically, we'd get 1/2 because base 1, height 1, area is 1/2. Done, okay? How else could we do it, though? Well, what's an antiderivative of x? Okay, 1/2 x squared, and then plus c. Okay, now, as we saw last time, are we convinced that in the situation where we have a definite integral, that means that there's a number at the top and the bottom, do we need the plus c? No, so I'll blow it off, okay? And then the fundamental theorem says that this integral that we were looking for, we can solve by finding an antiderivative and then plugging in the numbers at the top and the bottom in the correct way. Okay, what is the correct way? Plug in the top, plug in the bottom, and subtract in that order. Okay? And then just do the arithmetic and you get what you get. Now in this case, the arithmetic works out really easy, and sure enough, we get 1/2. No shocker, right? Because we already knew that the area was 1/2 just by geometry. Okay, so does that make sense? Oui? No. Okay. So let's do another one that we've done before. Okay, for this one, we had to do that Archimedes and kind of think about the parabola a little bit, but we ended up, and when all was said and done, we got 1/3. Okay, and if I were to do this the antiderivative way, well, what's an antiderivative of x squared? Yeah, 1/3 x cubed from 0 to 1. Okay, plug in 1, I get 1/3. Plug in 0, I get, well, 0. So this one just turns out to be 1/3. Well, good. That's exactly what it was supposed to be. Yes? Okay. So, the reason that this is so easy is because the step that takes the work most of the time is finding the antiderivative. Okay? And for these two functions that I picked, x and x squared, how did we find antiderivatives of those? Yeah, by the power rule in reverse, right? And then you have to do the whole socks and shoes thing that we talked about like weeks ago, right? No? You must have been, yeah, you dirty class skipper. Betas. You guys are the worst. Yeah. You're not a beta? Oh. Okay. Well, you're sitting too much over there with the betas, so yeah. Although Patrick, you would have loved it the other day and yesterday in my retro computing class, we were messing with changing the color on the screen of my 40-year-old computer, and by dumb luck, we ended up with like blue and pink, and I was like, this is way too beta for my tastes, and yeah, yeah, they are. But it's like you guys are about to have a baby, and you're just non-committal as to what you want to paint the nursery. Well, yes. I mean, if with an unborn baby, there's a good reason for not assuming that because it, I don't know, hasn't been born yet, right? All right, so let's do some more of these, right? Let me just for giggles here, not do 0 to 1 anymore because that makes the arithmetic too easy. Okay, so if we were to sketch geometrically what we're finding here, what's the graph of e to the x look like? Looks like that. Okay, and we're finding that area. Now, there's not any geometric formula that we know that's going to save us here. Okay, just sorry. But do we know an antiderivative of e to the x? Yeah, it happens to be its own antiderivative. Okay, what two functions have that property, that they are their own antiderivatives? E to the x and not natural log, because what's its derivative? Which is not itself. Okay, so e to the x is one such function. What's the other? Not quite. What's its derivative? Which is not itself. Last time I checked, 1 and 0 are in fact different numbers. Okay, but you're on the right track, Julius. You're very much on the right track. Help them out, guys. How about just 0 to begin with, right? Because what's its derivative? It's a constant, so its derivative is, which is itself. Done, right? Okay, now, which of those two functions is actually interesting? Yeah, I knew you guys would say that. 0 is pretty interesting. Let's be fair, right? Okay. So, but e to the x is the other such function, okay? And this is one of the things that makes the number e so special, is that e to the x is the function that has this property. Not 2 to the x, not 3 to the x, but e to the x, okay? All right, so what do I have to do here? If I know that e to the x is the antiderivative of e to the x, now I need to plug it in, okay? And what do I get? Not quite. I can't subtract exponents like that, bro face, right? I really can't do much. I can write it as e squared minus e, or I could go ahead and factor out an e if I wanted, right? But, okay, that's about the only thing that we could do at this point is, like, if we want the exact answer, there it is, right? Now, if we want a numeric approximation, okay, which is useful, right, to say, like, looking at our picture, right, is our formula, or like, I mean, my sketch is terrible, okay? If we did like a proper sketch of this where the axes were all like, the scale was all nice and stuff, then we could look at the picture and say, yeah, it's about whatever, right? All right, but e squared minus e, or that factored version, there's nothing better we can do there. Unless you want to plug in a calculator and get a numeric approximation, but we'll leave it as it is there. Okay, Gucci? All right, so let's turn this up a notch, right? Right now we're having, honey barbecue. Yeah, honey barbecue is pretty tasty, but let's spice this up a little bit and get some like buffalo mild going on, maybe medium. All right, so let me change the question. Um, let me do e to the 2x instead. Okay, again, there's no geometry formula that's going to save us, so we're hosed there. So what's the only other trick that we have up our sleeve so far? Using our brains with antiderivatives. Okay, so your quest, should you choose to accept it, is what is an antiderivative of e to the 2x? Okay, what's your initial gut guess going to be? Huh? 2e to the 2x? Okay, e to the 3x? Antiderivative, yeah. Okay, so good point, right? So I just said, what's an antiderivative? You misheard me and said her derivative. Okay, what's the derivative of e to the 2x? 2e to the 2x. Okay. Um, so we want an antiderivative. So I want a function whose derivative is e to the 2x. Okay, what would the first naive guess be? Just e to the 2x itself, right? But what is the derivative of that? As you just said, it's 2e to the 2x. But that's twice what it's supposed to be. So that's not quite the right answer. But what could we do, Mark? Let's throw a 1/2 out front. And what does that equal? Wow. Okay, so let's think about what we just did. Okay, what was the problem with 2x versus x? Yeah, what's the derivative of 2x? 2, not 1. Okay, and so if we just naively guessed our antiderivative here, we were off by a factor of 2. And where did that 2 come from? It came from the chain rule. Yes? So could we maybe kind of think about doing the chain rule backwards? So if the chain rule tells us that we need to multiply by 2 for derivatives, what should the chain rule tell us for antiderivatives? You do the opposite, which in this case would be division. Okay. Now, asterisk, big asterisk, and we'll talk about this in a moment. That only works if the thing that you're off by is a constant. If there's an x or something that you're off by, can't do it. I'll show you one in a minute. Let's finish this one and then we'll go there. Okay. Okay. So do you guys now buy that the antiderivative that we're looking for is this? Or I'm sorry, it should be from 1 to 2. Okay, do you guys buy that we've got the correct antiderivative? Okay, so how did we cook that up? For lack of a better way of putting it, it was guess and check, right? We tried something, it wasn't quite right, so we made a minor adjustment and it worked, right? Wasn't 100% guess and check, right? We weren't just stumbling around in the dark to find a function, but it was, still kind of guessy and checky. Okay. All right, so we buy that. Well, now that I've got the antiderivative, now what do I have to do? Just plug it in. That's not too bad. All right, so what do I get if I plug this in? E to the 4th minus 1/2 e squared. Okay, and again, that's just some number. I don't know what number it is. If I wanted a numeric approximation, bust out the calculator. But I'm perfectly content with the answer as it is. Okay, with maybe one other thing we could say here. We've got this subtraction. Basically, almost all of these are going to end up with a minus sign in them. Is this number positive or negative? Why? It is, but e is a constant. Okay. Okay. And it's more so, though, because e is bigger than 1, right? Because if e was less than 1, when you raise 1 to the 4th, it actually gets smaller. Okay. But yeah. But since e is like 2.7-ish, right? We know that e to the 4th is way bigger than e squared. And therefore, the stuff that we're subtracting is not as much as what we were subtracting from, and so this number is positive. Okay. Now, if we had graphed this function, would that fact have been obvious? Well, it should have been. What does the graph of e to the 2x look like? Right? And if I go from 1 to 2, okay, and standard SAT rules apply, figure may not be drawn to scale. Okay, you guys remember doing, actually, how many of you guys were able to skip the SAT because of COVID and not have to do standardized testing? Did anybody not take it at all because of the pandemic? No? Okay, well. Hmm? Well, okay, back in my day when we had to walk uphill both ways in the snow to get to the SAT and do it on stone tablets, I remember it always saying figure not chiseled to scale. The grids? Okay, well, that's pretty clutch. Okay, but we know it's definitely positive because where is the area that I just sketched out? Is it above the x-axis? All of it is, right? Now, if some of it's above and some of it's below, maybe if you kind of really think about it, you could figure out which one outweighs the other, but not necessarily. That would depend on the graph. Okay, so so we should get a positive number, and we do. I know. I'll send you the bill. Okay, so great. So let's return to what I started with, which is what happens if you're off by something other than just a constant, okay? And for that, let me actually return to our old friend from last time. I mentioned this guy, okay? And let me just well, we don't need to even worry about the numbers, the 0 and 1 or whatever, right? The bounds, okay? If I don't have the numbers at the top and the bottom, oops, sorry. Then this question is asking, what's the antiderivative? Okay, and here I do need to put the plus c. Yeah. Okay, maybe, right? So what's the derivative of, so let me just guess here. Let me say that I guess this. What's f prime? E to the x squared times 2x. Okay, is that what I wanted? No. Okay, so if we did like we did before, let's modify our guess to be, well, what's the problem? We're off by a 2x. Like last time, we were off by a 2. So why don't we say, okay, I see ya. I'll try this. Right, because then the 2x would cancel with the 2x? No. Okay, because how do I have to take the derivative? And in fact, let me call this not f, but g. Just give it a different name. What is g prime? What do we have to do? The quotient rule. Why do we have to do the quotient rule here? Well, there's a thing in the bottom, but more so than that. Keep talking. There's an x in the bottom, right? If it's just a constant in the bottom, we don't need the quotient rule, okay? Because if we did it, what's the derivative of the bottom? 0, and so half the quotient rule just disappears, and we don't have to worry about it, okay? But here we don't have that luxury. Yes? Okay, so what's the derivative of e to the x squared over 2x? Well, what's the quotient rule say? Low d high minus high d low all over low squared. Is that equal to e to the x squared? No. Okay, so our guess and check trickery that we played a minute ago with the numbers, like the 2 and the 1/2, that kind of thing, only works if it's that you're off by a constant. Were we off by a constant here? No, we were off by something that involved an x. Okay, so this doesn't work. If we return to the question, there is no antiderivative of that thing that I can write down. Okay, and this is what I was mentioning last time with the discussion of elementary functions. Okay, so if I take, let's just recap what we said there. If I take every polynomial you could ever think of, everything involving square roots, all the trig functions, the natural log, e to the x, every function you know, and then you think about how you can combine them algebraically using addition, subtraction, multiplication, division, and also function composition. Okay? That's a crap ton of things you could build, right? This gigantic pile of things. If you take the derivative of such a thing, you land back in that same pile. Proof, the quotient rule, chain rule, and product rule exist. Okay? And think about the quotient, product, chain, all of those rules. What do the answers look like? They're just combinations of addition, subtraction, multiplication, division, and function composition of the derivatives of the pieces that you put together, of the things that you built your big function out of. Well, since those methods of combination are already how we generated our pile, we haven't left our pile. Okay, that's not true for antiderivatives. There are some functions whose antiderivative is not somewhere else in that pile. It's in a bigger pile over there. And this function, e to the x squared, is one such function. Okay, now it shouldn't surprise you to know that there are infinitely many such functions. I mean, if there are infinitely many like easy functions, there's probably even more infinitely many not so easy functions. Okay, and the terms we have for this is the pile that we've constructed are called elementary. And if you leave that pile, you are now in the realm of what we call special functions. Okay, and this function is an example of a special function. Okay, and like I said, if I put a minus in front of the x squared, this thing actually, if you graph it, you get like a bell curve shape. And guess what the bell curve in probability is defined as? This, but with a few extra constants just to kind of doctor it up a little bit. Because in probability, what does the bell curve have to have? What properties does it have to have? Yeah, well, okay, so we call it the normal distribution, but what's the probability of everything happening? 1, right? And what's we worry about the mean and the standard deviation and all of that stuff. Well, I would have to doctor this up a little bit to make sure that the total area underneath of it is 1, because that makes sense in probability. Okay, but that's a pretty easy thing to fix. I also could scale it and shift it and stuff to get the standard deviation and the mean to be whatever I want, right? But it's essentially this function. No antiderivative. Sorry. Well, that really sucks, because guess what? Finding probabilities in real world stuff involves integrals. Okay. How many of you guys took stats in high school? Right. So we just draw a normal distribution. Okay. So let's say, oops, right, something like this. And our mean is wherever they're in the middle. Okay. Good. So let's just take sort of an example of something that's relatively normally distributed. So like the average height of an American adult male. Okay, what's maybe a reasonable guess for the average? 5'9", 5'8". Okay, so let's just say it's 5'9". Okay, just whatever. What's wrong, Patrick? Yeah, well, it wouldn't surprise anybody to know that Patrick is in fact below average. Right? You wouldn't have been able to go to school at Lake Wobegon High. How many of you guys have ever heard Prairie Home Companion on like NPR, this old radio show? So he talks about Lake Wobegon, this fictional town in Minnesota where all the children are above average. Okay, you see the problem with that statement, right? How can everybody be above average? That, breaks the definition of average. Okay. Um, anyway, so yeah, so let's just say it's 5'9", whatever. Okay. And then I'm asking the question, what is the probability that if we randomly select an American adult male, that their height is, say, I'm just going to make up some numbers here. Okay, let's say I want to know what's the probability that I randomly pick a guy and his height is between 5'9" and 6 foot. Okay, it does depend on a whole lot of that stuff, but in terms of calculus, what we're actually finding is an area between and this of this function. Okay, that's how probability in a continuous distribution is defined. Okay, now, is this truly a continuous distribution? No, because how many men are there in the country? Right, there's a lot, but it's a finite number. Okay, but if you've got 100 and something million guys, uh, can you approximate that with a smooth curve? Yeah. Now, if we started talking about what's the average height of you guys sitting here in this classroom, I wouldn't be able to do that, right? Because we got, like how many guys, how many people are in the room? 6, 9, 10, 10 people, and me, 11, right? That's not enough to really do a continuous distribution, okay? But several million, totally, okay? Um, so probability is asking you to find that area. The problem is there's no antiderivative for you to find and then plug in, period. There's no antiderivative for me to plug into, right? And I know a crap ton of calculus. Okay, so the moral of the story is, in this case, you have no choice but to do it numerically, okay? And find like a really, really highly accurate table of values, okay? Calculate z-scores, does that ring a bell? Yeah. And then look things up in your table of your z-scores and then do some arithmetic with that. Yeah, okay, but where did that 68% come from? It came from the tables, right? And that's assuming that you've got a clean multiple of a standard deviation. If you don't, then you got to go back to the tables in the first place. Okay. So what Mark's talking about is, what's the probability that you're within one standard deviation of the mean? 68 point whatever percent. Okay, that makes sense. Things are kind of clumped in the middle in the normal distribution, right? How many adult men do you know that are 3 feet tall? Okay, there probably are some, right? But it's the probability of randomly selecting one is very, very low. Okay. Um, and what's the probability of selecting somebody who's 12 feet tall? Basically zero. Okay. But what's the probability of selecting somebody who's 6 feet tall? Not all that horrible, right? I mean, because you guys know plenty of people that are 6 feet, and then some, probably. Okay. So the moral of the story here is, right, we need to be able to find these integrals, these antiderivatives, but we can't always do it. Okay. And so then what options do we have on the table? Well, let's actually return to where we started the discussion of integration in the first place. Could I approximate this by inscribing a bunch of little rectangles? Okay. Could I do a Riemann sum, basically? Or the trapezoid rule or something like that? Yeah. Okay. And do I want to do that by hand? Hell no. But what could I do? I could program a computer to do it. Okay, in which case I'll get highly accurate answers, and even though I'm maybe adding together 10,000 little rectangles or something, does that take that long for a computer to do it? No. Okay, so this stuff, like where the technique of just finding an antiderivative fails, either because you don't know enough math or there just isn't one, okay, one of the two, um, then the only resort you have is to do it numerically. Sorry. Not with 10,000. Okay. I might give you something where it's like, here's a thing, do 4 rectangles to approximate. Um, oh, okay. Good question there. Um, it, so let me actually rephrase the question and answer. What about if I don't even care if it has or it doesn't have an antiderivative, but I really want you to do the Riemann sum? Forget whether it does or doesn't have an antiderivative, right? To do a Riemann sum, right? Okay, so what I would not do is give you an integral and say, not tell you like, hey, there's no antiderivative here, and so you have to know that somehow and then go to a Riemann sum. No, 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 no. That I wouldn't expect. But if I did say, here's a thing, I want you to do a Riemann sum with 4 rectangles, go. Here's the function. Here's maybe even a nice sketch of the graph. Okay, that totally, right? Because there I'm not asking about antiderivatives so much as about the concept of a Riemann sum. Okay, does that make sense? Oh, and that actually reminds me about, well, 3 things. What are we doing on Monday? Okay, which, you know what would be really nice is if the professor had finished grading the last one before he gives you a next one. Yeah, and you know what the professor hasn't done? Finished grading them. Okay, because I know I'm a total bruh-face. Okay, but I will get them done and back to you. Okay, but I'm going to give you guys a bonus here, multiple bonuses. It's a season of bonus. Okay, it's like Oprah's like favorite things episode. Right, everybody gets a bonus. Okay, so what time is SI on Friday, Sunday? Whatever you put in the email. Well, what is it? 7. That's correct. Okay, so at 8 o'clock is SI finished? Yeah. So what should we do from 8 to 10 on Sunday night? No, I'm not that mean. This is the season of bonus. What about we have Dr. McKinney's version of SI, where I'll definitely have handed back all the exams and I'll answer any questions you might have over them. Deal? Okay, we'll just do it here. I'll reserve the room so we're all set. Okay? At 8 o'clock on Sunday. Does that sound okay? Maybe I'll even go to the store and get like cookies or something. Yeah. Mhm. Yeah. So you got something wrong, not understand what you should have done, I'll explain it to everybody. Sure. Although it really shouldn't be too much explanation needed there. Just sit your ass down and memorize it. Okay, there's your explanation. Yeah, and everything is a combination of those basic ones. Okay, I will even explain that magic combinations. Okay, so there's bonus number 1. Bonus number 2 is, how many bonuses did I say there would be? Okay, well, so maybe the cookies are bonus number 2. I don't know. Right, bonus number 3. So if on Monday, what are we doing outside of class? An assessment. What are we going to do on Friday? A bonus assessment. Okay. So Friday next week, I'll give you one in class because we'll have time for it over just the integration stuff. So it'll be a little shorter and that way it'll fit in class. Okay. And then when's our final? Tuesday at 9 a.m. Okay. So on the subject of that, this is the not so bonus part. Uh, all of the infinities are up for the rest of the semester. Everything's there. Okay. So there's not going to be any more added. And all of the tasks are even up, although I need to give you guys some guidelines for the final reflection paper. Okay, but that shouldn't be rocket science. Um, so when does Edfinity lock everything? Tuesday of finals week at 9 a.m., which is the exact moment I'll be handing out to everybody your exams, right? Now, the last thing would be, let's say that you really nail it on Monday and Friday next week, and you basically have enough assessments passed and you've got enough infinity points to have an A according to the syllabus. Do you have to come to the final? Nope. Okay. So let this be this is the third bonus, right? You might not have to come and take the final. And if you do, that's okay. It'll just be a big assessment, right? Mhm. You got to get what, like 90 something percent of them? The homework points. Yeah. Or 95% on literally every assignment. However, the average, I mean, if you got 100% on half of them and 0% on the other half, what's your average? Basically 50, right? That's not good enough, right? Yeah, so basically all it does is it counts up the number of points you got and divides by the number of points that were available, right? That's it. Well, okay, and I am more than happy to answer questions if you're stuck on one of these. Okay, there's a fourth bonus, Mark. Ask and ye shall receive. Okay. Okay, so I think that's it for now. Monday, and we'll talk about the technique of substitution, okay, which is basically uh, how to make this guessing and checking routine a little bit less guessy and checky. And I say a little bit because there still is some guessy and checky. But also the functions that we were dealing with today were all relatively nice. I'm going to make them nastier, okay, but we'll still be able to do them using this technique. Now, integration is a genuine art form, okay? What do you think the first third of Calc 2 is all spent doing? Different techniques of integration. There are just tons of them out there, okay? Use substitution, or the method of substitution, okay, is basically the first like technique that's worth being called a technique that you learn, and it tends to be the very last thing you do in Calc 1. And then the next thing that you learn in Calc 2 is sort of how to do the product rule in reverse, and that's called integration by parts. That's the very first thing you cover in Calc 2. That's a pretty standard split point. Okay, kind of makes sense? All right, so I will send out an announcement about the Sunday night thing. We'll just do it here because we certainly have the space. Yes? Like fix it? Maybe I'll let you do that. Like fix an old task that, yeah, fix an old task that you submitted but needs to be corrected. Maybe I'll even let you do that. This is the season of bonus, gentlemen. All right. Yeah. Y'all have a great rest of your Friday and weekend. I'll see you Sunday, if not sooner. And